So goal is to find approximation of u double prime at x naught, and I'm going to prescribe up front which points you're going to use to get the approximation. So u of x naught, u of x naught plus h, which you can think of as x1, and u of x naught minus h, which would be x2. So the form of the approximation is a0 u of x0 plus a1 u of x1 plus a2 u of x2. And I'm going to add a requirement. I also want not just the approximation, but also an error formula. So I'm going to do both at once. So what I'm going to do then is rewrite this as using Taylor expansions of these two around x naught. So everything's expanded around x naught. So I have my approximation is equal to, and I don't know just yet how many terms I'm going to need, but let's see what happens. So first term we can't do anything with, it's just as is. And then for the next term, I'm going to have a1 times, so I expand around x naught. Now x1 is x naught plus h. So that spacing goes here. I'm going to have 1/2 h squared u double prime. So we definitely need to go out this far, but I'll need to go out further if I want to get an error term. So I have h cubed u double prime x naught, and I'll go out one more, u quadruple prime of x naught, and so on. All that's times a1, and then plus a2 times similar expansion around x2, evaluating x2 but expanding around x naught. So x2 is x naught minus h, so I'm going to have minus h throughout here. Write these a little more compactly. Okay. Now, when I combine these, I want to get u double prime of x naught plus terms that have a positive power in h of them, so that as h goes to 0, any error terms will go to 0. And I want as many other terms as possible, aside from u double prime terms, to go away. But I only have 3 coefficients, a0, a1, and a2. So to have a unique solution, I really can only impose 3 conditions. So if I look at the terms involving u of x naught, I want these to go away. So I need a0, u of x naught plus a1, u of x naught plus a2, u of x naught to be 0. But I can factor u of x naught out of that, so I can just say a0 plus a1 plus a2 equals 0. So that's one condition that the coefficients have to satisfy. Then when I move on to the u prime terms, I want those to go away also. So I have a1 hu prime of x naught plus a2, or minus a2 hu prime of x naught is 0. So I can factor u prime of x naught out of that, and that gives me a second equation. a1h minus a2h is equal to 0. I could also factor out an h. The reason I'm not doing that is to be more consistent with what's in the notes. If we didn't have uniform spacing, then I couldn't factor that out anyway. And then second derivative terms, I have coefficients multiplying u double prime of x naught, and I want those to add up to 1. So I have, let's separate these. So I have a1 h squared over 2 u double prime of x naught plus a2 h squared over 2 u double prime of x naught is equal to 1, because I want to be all combined to get me just plain old u double prime of x naught plus our stuff. Now what I can do is I can not equal to 1, equal to 1 times u double prime of x naught. That's what I want those terms to become. Now I can divide both sides by u double prime of x naught, and then I can multiply both sides by 2. So then it gets a1 h squared plus a2 h squared is equal to 2. So these three equations are exactly the equations that appear in the notes. So we can go ahead and solve that system. From this one, we can see that, but if we go ahead and divide by h, we see that a1 is actually equal to a2. And then from here, we have a1 plus a2 must be equal to 2 over h squared, but a1 must equal a2. So that tells us a1 and a2 are both equal to 1 over h squared. But all of the coefficients, a0, a1, a2, must sum to 0. So that's why a0 is minus 2 over h squared. So now if I bring these coefficients, so now I have my stencil. So that is my approximation. But now what I'm going to do is go back to this and see what my error is. So if I go ahead and fill in the values of these coefficients in here, then what I'm going to get is, and I also fill them in on the left side. So on the left side, I'm going to have minus 2 u of x naught plus u of x naught plus h plus u of x naught minus h all over h squared. So this left side over here becomes this by filling in a0, a1, a2. And then over here, well, these coefficients were designed to make all of these terms go away. These go away. And then the coefficients of this end up becoming 1. So these give me u double prime of x naught. But now I can look at these other terms to get the error. So not knowing what my order of accuracy is, if I just have a1, so I have plus a1, which is 1 over h squared, times this term right here, h cubed over 6 u triple prime. And then a2 is also 1 over h squared, times the same thing, but with a minus. But then, these terms, no matter what, they're going to cancel. So the symmetry of the stencil using x naught, x1, x2 that are equally spaced causes that to happen. And so then if I move on to the next term, I can see what my error is going to be. So a1 is, so I have 1 over h squared, h to the 4th over 24, fourth derivative, and then same term again, exactly, same sign even. So what I get is, so my approximation gives me u double prime and x naught plus this leading error term, which condenses to h squared over 12, fourth derivative at x naught. And then there are other terms that would be over at least h cubed, which I'm neglecting. But normally these are written as my exact expression is equal to my approximation plus the error. So really the error is minus h squared over 12. So by writing out the Taylor expansions and then using those Taylor expansions to impose conditions on the coefficients that must be satisfied, like making all these terms go away, making these terms times their coefficients add up to just 1 times the derivative you're trying to approximate. Then, however many coefficients you have, that's how many equations you're allowed to impose to get a unique solution, a unique stencil. And once you have those coefficients, you can go back here, look at these terms, and see what your error is. If I had chosen any other spacing, like x0, x01, x2, not equally spaced, these terms would not have canceled, and I would have gotten only first order accuracy. But symmetry, like I said, you get lucky, and we get second order in this case. But not, and when you have symmetric approximations like that, you generally get 1 order higher than you would expect just from the system of equations.